drift current? What is diffusion? What is diffusion current? So drift is the movement of charge caused by an electric field. And either what will be drifting is either an electron or a hole. And these carriers, they move with different speeds. So there must be a potential difference between the ends of a conductor if we want current to flow. So again, we rely on the very basic physics we learned in secondary school, that velocity, we can also get velocity in terms of acceleration and time. What is acceleration? Is velocity divided by t. So velocity will be acceleration times t. And we know from Newton's second law of motion, Newton's laws of motion tell us that acceleration, which law is that? The second law. And acceleration is force divided by mass. Now, slightly more advanced physics will tell us that this force is related to electric field, and it is Q, where Q is the charge multiplied by the electric field. So force is charge of the carrier multiplied by the electric field. The whole of this equation can be rewritten like this: QT E divided by M gives you the drift velocity. So we realize this one, this QT, Q is constant. Q is constant, mass is constant, and the time in question is also constant. And therefore, we can say the drift velocity is proportional to the electric field. So this is behaving like a constant Qt divided by M. And we can replace Qt over M by a constant we call mu. And in electronics, this mu is known as charge mobility. Charge mobility, whose units are, if I make mu the subject of the formula, we'll have mu having units of v divided by e. We know the units of velocity is meters per second. Units of electric field are volt per meter, because we said electric field, you can see it from there. So this equation 5.6 is also giving us the ability to measure the mobility of a charge. So this equation, if I want the mobility of an electron, then mu becomes negative. Therefore, we can determine the drift velocity in charge of the electron mobility and the electric field, giving us equation 5.7. Please, I repeat once more, get the notes which I send your class rep, and slowly go through this to be able to understand. But at least what we are doing now will make that work simpler for you. And we can also, the same equation, if you see 5.6, if we are talking of O's, now mu, this letter, this mobility, charge mobility will be mu p. For electrons, we call it mu n, and we bring in the negative sign. this mu for O's will be mu P, which we have here 5.8. So the drift velocity will be mu PE. And we remember how do we define J? J we said is current density. So this drifting of electrons produce what we call drift current density. What is the drift current density is I divided by A. If we check back here, J is this NQVD. Now, if you can write down, if we can write down equation 5.4, we have J being equal to NQVD. And in equation, in this equation, either 5.7, 5.6, we have the value of V. So I can put in 5.4 the value of V as being equal to this. Therefore, we get this equation. For electrons, you'll be having Ne. Please compare this. It's not difficult to see this. We have been given the value of V, and equation 5.4 gives us the value of J. J is this. So I replace in equation 5.4 with the value of V, where V we have obtained for electrons is negative mu A. So you see, so we end up getting the current density due to electrons as En mu E. What is E? Is the electronic charge. N is the electron density. Mu is charge mobility. E is the electric field. Where did we get this negative? When we have negative E, and we multiply this, we take out this N, this E out, and then we bring in V for electrons. What is V for electrons? Is here. Oh, that's what's happening. My slides can't move. Remember, V is negative mu N multiplied by E. So when I put V having negative mu N, mu E, we have this negative, and the negative brought in by this one, giving us positive. And that's how we have En mu E. 5.9 is it's quite a challenge. But if you are just systematic, writing down everything, you will see. But I think at your level, I can never ask you to derive these equations. But the end result of these equations, you can be asked to use them. My slide can't move. What is happening? Okay. So the total drift current, we write it like this. If we compare, and this is the drift current density due to electrons, drift current density due to O's. So if I combine, these two equations, 5.9 and 5.10, I get the total current. The total current will be this current density plus this current density, which is this plus this. See it here? It gives us this equation, J equals to this. And I can replace, if you see here, there is E n mu n, E p mu p, and I can take E common. E is common to these two terms, and whatever is inside the bracket will now be represented by this letter sigma, where sigma is E n mu n plus EP mu p. So this sigma is what we call conductivity. And we also relate conductivity with what we have had before in secondary school, resistivity. Conductivity is the reciprocal of resistivity. So we should be able now to answer this question. Any student who can volunteer to read this? Example 4.2. Any volunteer? Yes, read, please. Read.
Calculate the drift current density of silicon at 300 Kelvin doped with arsenic atoms at a concentration of Nd, which is equal to 8 times 10 power 15 centimeters per centimeters cubed. You are given that the mu n is 1350 centimeter per velocity seconds. Mu p is 480 centimeters per velocity seconds, and the applied electric field is 100 V per centimeter.
What is V? This V is capital V is not a small v, so this V is false. We remember mu is the charge mobility. So we are given the donor concentration in brought in by arsenic. We are given the charge mobility due to charge mobility for electrons is that. The charge mobility for us is this. So this is centimeters squared per volt per second. That's how we read. This one we read as 8 times 10 raised to power 15 per centimeter cubed. Okay, so the question is calculate the drift current density. That is what we want to calculate is J, this J. Okay, so what do? We have measurable, and we remember from the mass action law that N is what gives us most of the electrons come from the donor atoms. Therefore, we can say N, small n, is approximately equal to ND, which we have been given. And the P, we get it from mass action law, which is the intrinsic carrier concentration squared divided by the donor concentration. So do we know this one? I think this one was not given, but in a serious question, you will be given this. You are not expected to cram constants. So Ni, that is the intrinsic concentration, is 1.5 times 10 raised to power 10 for silicon. That is for silicon, okay? So we get N is that, P is this, and therefore we can use this equation. Which equation? This one. Placed here to get J, okay? So we see conductivity is given by E n mu n plus EP mu P. And E is the electronic charge, which is 1.6 times 10 raised to power negative 19. So you can check through whether this calculation is correct. It gives you the conductivity of this material. And we get back to this here that once we know the conductivity and multiply it with the E, then we get the current density. So we have sigma, which is the conductivity. When you multiply sigma by E, and we are given E is 100 volts per centimeter, we get the current density. So I think we want to stop there. What I want you to do in your own spare time, you have to devote a lot of time to understand this. Check whether you can understand example 4.3 on your own, and then you try and tackle diffusion current, which eventually gives us this very important equation, this one. And also defines what we call thermal voltage. So the objective of going through this section dealing with diffusion current is to be able to determine thermal voltage and build in potential in the depletion layer. So I think class rep, once more, please share what I sent to you with your classmates. We will meet for the cut during the physical class. Of course, when is the